Generative models have revolutionized artificial intelligence, enabling machines to create new data that's sometimes indistinguishable from real-world examples. Today, we're going to dive into the implementation of deep learning generative models, focusing on how deep neural networks effectively capture complex variations in data, like images and language. So far, we've explored the transformative impact of deep learning on generative modeling, particularly through techniques like variational autoencoders, or VAEs, and generative adversarial networks, known as GANs. We've seen how VAEs generate realistic data by encoding and decoding inputs, illustrated with practical coding examples that hopefully made things clearer for you. Plus, we've discussed the diverse applications of VAEs in fields like medical imaging and anomaly detection, showcasing their versatility. Overall, these generative models present exciting opportunities for creativity and innovation across various domains. Now, let's roll up our sleeves and cover how to implement these models in a practical setting, specifically using Python and PyTorch. So, let's get started. Now, let's implement the generator and discriminator models for our GAN. First, we'll create the generator class, which is responsible for generating synthetic images from a random noise vector. The generator uses a sequential model made up of multiple linear layers with ReLU activation functions, helping it to learn those complex patterns in the data. At the final layer, we apply the tan activation function to ensure that the output pixel values of the generated images fall within the range of -1 to 1, which is really important for proper image scaling. Next up, we define the discriminator class, which evaluates images and classifies them as either real or fake. This model has a similar structure, with several linear layers mixed in with Lie-ReLU activations, allowing for better gradient flow during training. The final sigmoid layer gives us a probability indicating whether the image is authentic. With both the generator and discriminator models in place, we can now effectively train these networks in an adversarial way. This back and forth helps them enhance each other's performance iteratively, leading to the creation of those high-quality synthetic images. Isn't that pretty cool? The figure displays two grouped sets of bars that summarize model-level performance and task-specific effectiveness. On the left axis, we've got model performance scores. GAN sits at 90%, while VAE holds 85%. This shows that GAN enjoys a modest advantage of about 5 percentage points in our chosen performance metric. Now, both these models are performing at a high level, indicating strong overall capability. On the right axis, we see application effectiveness scores, which show image generation at 75% and anomaly detection at 65%. Here, that 10-point gap emphasizes that these models are relatively more effective for image generation tasks compared to anomaly detection in this context. So it makes two clear points. First, while GANs have that slight edge in raw model performance, especially relevant for producing realistic images, VAEs remain competitive. And second, we see that application-level effectiveness is lower than model performance percentages, meaning that just because a model scores high doesn't mean it'll perform equally well across all downstream tasks. From these patterns, we can conclude that for tasks prioritizing visual realism, like image generation, the GAN is the stronger candidate. Thoughtful pause. However, for tasks that require structured latent representations or probabilistic reasoning, like anomaly detection, the VAE still shows utility, even with lower application effectiveness. This really suggests that when choosing a generative model for a specific application, practitioners should carefully weigh both the reported model performance and the task-specific effectiveness. Next, we will implement the training loop for our GAN, which will involve several key steps to maximize the performance of both the generator and discriminator networks. First, let's load the MNIST dataset and apply some necessary transformations, like normalizing the pixel values. This step is important to improve training stability. Now, after loading the dataset, we'll initialize both our generator and discriminator instances. It's crucial to set up the loss function. In this case, we'll use binary cross-entropy. This helps measure how well the generator is at fooling the discriminator, and vice versa. We also need to configure optimizers for both networks using the Atom algorithm, along with setting learning rates and momentum values to facilitate effective training. Now, here's where it gets exciting. Inside our core training loop, we iterate through the dataset for a specified number of epochs. In each epoch, we'll process batches of real images and create labels for both real and fake images to aid in the training process. First, we start by training the discriminator with a mixed batch of real and generated images. This helps continuously enhance its ability to tell the difference. Then, we train the generator, aiming to optimize its output so that the discriminator mistakenly identifies the generated images as real. After each epoch, we'll print the loss values for both models, providing us with insights into their learning progress throughout the training process. This feedback loop is essential. It lets us know how well our networks are learning. Now that we've trained our GAN, it's time to visualize the generator's progress. Next, we'll write a function to generate and save images during training. In this function, we start by creating a random input noise vector, z, using a normal distribution. This vector serves as the input to our generator, which means it produces synthetic images. After generating these images, we reshape them for proper display and then use the makeGrid function to arrange them in a nice grid format. Normalizing the images ensures they're in a suitable range for visual representation. We'll even add a title indicating the current epoch number, and to keep things tidy, we'll disable the axis for a cleaner view. Finally, the generated grid of images is saved to a file with a unique name for each epoch, allowing us to track the evolution of image quality over time. To utilize this function effectively, we will invoke it at specific intervals in our training loop, specifically after every 10 epochs. This ensures that we capture the progression of the generator in producing realistic images as training advances. This monitoring is crucial for assessing the effectiveness of our GAN. Now, let's implement a simple variational autoencoder, or VAE, in PyTorch for image data using the MNIST dataset. First, we need to define the VAE class. This will inherit from PyTorch's nn.module. In the constructor, we'll set up our encoder and decoder architectures. The encoder has a linear layer that brings down the input size from 784, which is what we get from 28 by 28 images, all the way down to 400. Next, we apply a ReLU activation function. After that, we have two separate linear layers, one to compute the mean and another for the log variance of our latent distribution. Both of these layers compress our data down to a size of 20. That defines our latent space. Now, we move on to implementing some key methods: encode, reparameterize, decode, and forward. The encode method takes the input and produces the mean and log variance from the encoder. Then comes the reparameterize method, which samples from the latent space using the mean and log variance. This is crucial as it allows gradients to flow during training. So, we get our decoded samples in the decode method, which works to reconstruct the original input from those sampled latent values. And finally, the forward method ties it all together, orchestrating the encoding and decoding process. It produces both the reconstructed data and the latent variables, which are essential for loss calculation during training. There you have it. That's our foundation for a variational autoencoder. Now, let's implement the training loop for our variational autoencoder, or VAE. First, we'll load the MNIST dataset using a data loader. This allows for efficient batch processing by shuffling the data and setting a batch size of 64. Next, we initialize our VAE model and set up the atom optimizer, which will help us adjust the model parameters as we train. In the training loop, we define the number of epochs we want to iterate through and begin processing each batch of real images. For every batch, we reshape the images into a vector format that's suitable for our network. Now, to prevent the optimizer from carrying over gradients from the previous iteration, we first zero the gradients. Then, we execute the forward pass, generating reconstructed images along with the mean and log variance of the latent variables. We compute the reconstruction loss using binary cross-entropy, ensuring our model learns to recreate the original images accurately. Additionally, we calculate the KL divergence to regularize the latent space, nudging it towards a standard Gaussian distribution. Now, the total loss is simply the sum of these two components. This total loss is what we use to perform backpropagation, updating the network's weights. After each epoch, we print out the loss to monitor our training progress, allowing us to see just how well the VAE is learning to generate data that's consistent with the original dataset. It's quite exciting to watch this all unfold. Now, let's implement the function that will visualize the reconstructed images generated by our trained variational autoencoder, or VAE for short. This function is called Visualize Reconstructed Images. It begins by disabling gradient calculations. Why? Well, this helps us generate samples efficiently without impacting our model parameters. Next, we create a random latent vector, which we'll call Z. This serves as the input to our decoder. With this setup, we're going to generate a specified number of images. Why do we do this? It allows us to see how well our VAE has learned to replicate the input distribution. Once we have those generated images, they need to be reshaped to match the original input dimensions. We then arrange them into a grid using the makeGrid function. This arrangement makes visual comparison much easier. After that, we utilize plt.imshow to display this grid. We also configure the titles and axes for clarity, of course. This entire visualization process makes it much easier to evaluate how effective our model is in capturing the various features of the data. So, by calling this function after training, you can see firsthand the results of your VAE's ability to generate new data samples. This will really help you understand how well your model is performing, as well as the quality of the output images. In conclusion, the implementation of deep learning generative models like GANs and VAEs really invites us to explore creative data generation. Whether we're synthesizing new images or uncovering complex data distributions, these models open up a world of possibilities. From art to medicine, you name it. Today, we've walked through how deep neural networks serve as the backbone for these generative models. We took a closer look at GANs, these remarkable adversarial networks that push their components to improve simultaneously, which is just fascinating. Then we pivoted to VAEs, where we emphasized probabilistic encoding and sampling within their architecture. And don't forget, by implementing practical examples in Python using PyTorch, we're really setting ourselves up to carry these techniques into real-world applications. As we continue our journey in this domain, there's still so much more to explore. We can dive into advanced techniques and tackle areas like conditional generation and monitoring model performance. So stay curious, keep experimenting with these tools, and remember, the only limit is your creativity.